Vanakkam. Welcome to this video on biomechanics. We have been looking at practical applications and how we can measure body segmental kinematics and how to represent them, how to plot them, and how to graphically represent them using software. We looked at some MATLAB examples of this in the previous class. In this video, we will look at the composite rotation matrix, that is a rotation matrix that has an angle or different angles about the three principal axes. So, in the previous videos we looked at rotations that happen only about one of the principal axes at a time. In this video we will be looking at what happens when a composite rotation happens, that is a rotation that involves rotation about all the three principal axes. How to convert rotation matrices to Euler angles, and how to measure relative orientations using rotation matrices, how to use rotation matrix to find orientation difference. This is what we will be looking at. Now consider this case where I am having an angle change or a rotation of psi, an angle of psi happening about the x axis, an angle of theta happening about the y axis, and an angle of phi happening about the z axis. For clarity, that is psi, that is theta, and that is phi. Just writing this for clarity. And let us say that the rotation is happening in the order x, y, z. What does this mean? Does it mean that first the x rotation is happening, and then the y rotation is happening, and then the z rotation is happening? Is that what it means, or what does it mean? Actually, x, y, z order of rotation does not necessarily imply a temporal order. It does not mean that the x rotation is first happening in time, followed in time by the y rotation, and followed in time by the z rotation. This is not what it means. What this means is the considered order for representation is x, y, z. Okay. This is the order of representation that is used. Okay. This does not necessarily imply or mean, and almost never the case, that this is the temporal order in which the rotation is happening. The rotation will happen in whatever order it happens, and it may not even happen about any one axis at a time. Simultaneously it might be happening about many axes, all of these three principal axes. So this does not imply a temporal order. Order of rotation does not imply a or does not imply temporal order, right. Now, but you still, for representation sake, you need to identify what is the considered order of rotation, that is x, y, z. That means the x rotation matrix followed by the y rotation matrix followed by the z rotation matrix is from right to left. Remember matrix multiplication, how does it happen? From right to the left. That is how it happens. Remember, from childhood, from high school, this is how we perform matrix multiplication. So if the order of rotation is x, y, z, then the z rotation matrix will come first, followed by the y rotation matrix, followed by the x rotation matrix. This will imply the actual considered order of rotation is x, y, z. That is what it means. And after some multiplication, after matrix multiplication, this is what I will get as the, this is what I will get as the composite rotation matrix. Looks like a very scary thing, right? There are many things and it is not clear how to identify the rotations about each by looking at this, because you are not just going to have this, you are going to have numbers. When you are measuring simultaneously about all these three axes using a measurement system such as an IMU, you are going to have some numbers that are going to be presented. How do you know what is the angle that is made about each of the principal axes so that you can plot, right? How do you know that? That is what we will see in the rest of the video. So, here rotation is happening about this green axis, right, and in this case rotation is happening about that blue axis, and here rotation is happening about that red axis, whatever that axis is, x, y, z axis, and here that is the rotation that is happening. Where is this rotation happening? About which axis? That is not clear, right. Let us play it one more time. In the first case, the rotation is happening about the green axis, is it not? In the second case, it is, one more time, it is, in the second case it is happening about the blue axis, and in the third case it is happening about the z, about the red axis, right. Now, what about this one? This is the composite rotation that we are speaking about. This combines rotation happening about all the three axes. In this case, maybe it looks like all the three axes are undergoing the same amount of rotation, but that need not be the case in real life. It can undergo different, and almost always undergoes different amounts of rotation about the three principal axes, which is why you are having psi, theta and phi as the three angles about the three axes. So, you are going to have a rotation that looks like this, right. The question is, how do you compute the rotation that is happening about each of the principal axes for your understanding and for your representation sake? Here it is simulated data, and so I am changing all the three axes simultaneously, and the code is just plotting this out, but it is difficult for me to visualize when this happens. Unless I understand the rotation that is happening about each of the axes, it is somewhat difficult for us to visualize. In this case, this is simulated data, so it looks nearly perfect and very symmetrical and very easy for me to understand, but real life that need not happen, right. So, because if this rotation matrix is the one that is being output by an IMU, then it is not clear for me how to visualize, or it is not very simple for me to visualize. Okay. How do I then look at? Well, it seems like there are ways in which I can find those specific angles. For example, I can start out with this. I am only having sin theta. So, if I am getting that element value, then I can find the value of theta as sin inverse, right. That will give me the angle about the y axis, for example, right. If this is the composite rotation matrix, remember this is true only for this order of rotation. Remember this is key. This composite rotation matrix works only for this order of rotation, not for any other order of rotation. Okay. So, this is an example. You cannot memorize this, for example. Remember this. Okay. So, the element 3 1 is minus sin theta. So, I can find theta as minus sin inverse of this rotation matrix element 3 1, right. Straight away, straightforward, I am getting theta. Now, are there other ways of finding phi and psi? Well, if I look at these two, 3 2 and 3 3, there is a common element cos theta between them. If I divide one by the other, cos theta is going to get cancelled, and I will have tan phi as R32 by R33. Once again, remember, this works only for this order of rotation, because for different orders of rotation you will have different composite rotation matrices. I will speak about that in just a minute. For this order of rotation I am having this composite matrix, and from that I can find phi as tan inverse of R32 by R33, right. Okay. Likewise, if I take these two, if I divide one by the other, I am going to get tan psi, and I can find psi as tan inverse of R21 and R11, R21 divided by R11. I can do something else. If I first find theta, well, if I first find theta, there are other ways of doing this. There is no single way to do this. For example, if I have found theta, right, using this method, then I can take this value, that is R32. R32 is sin phi cos theta, and since I know theta, I already know theta. How do you know? I just found it in the previous step. From that I can find sin phi as R32 by cos theta, where theta is already known from this step, from the first step. Likewise here also I can find cos psi as I can find cos psi as R11 divided by cos theta. So psi is cos inverse of R11 by cos theta. Theta is already known for me. There are many ways of doing this. There is no single way. This works for the most general case. So this is a simple case. So I can straight away take these elements, and I can straight away take R31, R32, R33 and R21 and R11, and I immediately get this, right. So using this I can find the angles, the Euler angles from the rotation matrices. This is using a manual method or an algorithm. If you are having the aerospace toolbox in MATLAB, by the way, this is not a default toolbox that comes with MATLAB, okay. If you have this toolbox, then converting from the rotation matrix to Euler angles is DCM to angle of the rotation matrix. You still need the sequence, because otherwise the system will not understand. You still need to say whether it is x, y, z or whatever else, right. So you will still need that sequence as an input to this toolbox, to this function DCM to angle, to compute your Euler angles. What is this DCM? DCM is this matrix of direction cosines, or direction cosine matrix, right. Direction cosine matrix to angle, that is another way in which you can represent rotation matrix, right. There is an issue that comes when you try to convert from rotation matrix to Euler angles, that is gimbal locks. This is a problem that we will discuss in much greater detail in a future video. For example, what happens here is that initially this blue frame, right, is at a different angle, then it goes and locks itself to, or aligns itself in line with the magenta frame now, right. In this case what happens is that the measurement will no longer have the same number of degrees of freedom as expected. It is not like there is a physical lock that is happening, but measurement will no longer be uniquely represented. There are some measurement issues that come into this picture. We will discuss this in much greater detail in future. So when you do this, you need to be a little cautious about the conversion from rotation matrix to Euler angles, because sometimes, so this is an issue that comes only when you are dealing with Euler angles, right, something to keep in mind. So when you are converting and when this gimbal lock happens, there is some uncertainty or some ambiguity about the way you represent data. You need to be sure about how you are representing this data, otherwise because you are only using software to plot, we will all use software to plot, like MATLAB. MATLAB will plot whatever is given to it, because it is not having a brain of its own, whatever data is given. Only as humans, as experimenters, we know that some sets of data make sense and some angles are impossible to happen. But the system does not know these things. Whatever is given to it, it will plot, something to keep in mind. Now, let us just briefly discuss this jumble log problem for the case when theta goes to 90 degrees. Suppose theta equal to 90 degrees or pi by 2 radians, right. In the xyz sequence, remember the sequence is xyz, okay. Then what happens to this matrix? Substitute everywhere theta equal to 90 degrees and let us rewrite this matrix. It is going to take a little bit of time, but let us do that. Cos theta, well, cos 90 is 0, and again the second element cos 90 is 0, minus sin theta is minus 1, sin 90 is 1, but it is minus sin theta, so that will be minus 1, and the next one is having sin phi sin theta cos psi, right. So, that will become, because sin theta is 1, that will become sin phi cos psi minus cos phi sin psi minus cos phi sin psi. Already I am getting some hints about what is happening, because this looks like a trigonometric identity, but let me proceed. The next one is cos phi cos psi sin theta. Sin theta is 1, so I am going to write this as cos phi cos psi plus sin psi sin phi. The next element is sin phi sin psi sin theta, because sin theta is 1, this will become sin phi sin psi plus cos phi cos psi. This is also looking like a trigonometric identity. The next one is cos phi sin theta sin psi, because sin theta is 1, that will become cos phi sin theta is 1 sin psi minus sin phi cos psi. The next one is sin phi cos theta is 0. The next one is cos phi cos theta, but for theta 90 degrees cos theta is 0. This is the rotation matrix that I get when theta goes to 90 degrees, as seen in this. The blue measure here is going to 90 degrees. When it goes to 90 degrees, this is what I will get. Let me apply the trigonometric identities that I know here, okay. What would that be? That would be 0, 0, minus 1. This one, what is this? This is sin phi cos psi minus cos phi sin psi, that is sin of phi minus psi, okay. The next one is cos phi cos psi plus sin phi sin psi, right, that is cos of phi minus psi, okay. The next one again is sin phi sin psi plus cos phi cos psi, that is again cos of phi minus psi, and the next one is cos phi sin psi minus sin phi cos psi, that is actually minus of sin of phi minus psi, okay. Then the next two elements are already 0, because cos theta is 0. What this tells me is that now the description of this rotation is dependent only on two angles. What are these two angles? Are actually only 1 degree of freedom. This 1 degree of freedom, it turns out, is this angle difference between phi and psi. Right. The difference between the angles, these two angles, is the only degree of freedom that appears to matter here. Right. Now, from this what I am understanding is that it appears like there is a reduction in the number of degrees of freedom. Earlier I had 3 degrees of freedom, now it appears like only this is all that matters for describing this rotation. And remember, this happens only when theta equal to pi by 2. What is theta? That is rotation about the second axis, second principal axis in this sequence, the y axis in this case. Okay. Now, we will have a longer discussion about this in a future video, but this is something that we want to keep in mind, that suppose theta equal to pi by 2, or suppose the second angle goes to pi by 2, then the whole system or the whole representation breaks down, and we are going to have quite a bit of complexity that is going to appear in this, or quite a bit of ambiguity that appears here. Okay. This is called gimbal lock. Now, I am interested in measuring relative rotations. This is what I am interested, because what I am working on is finger kinematics, orientations of finger with respect to each other. I am interested in relative rotations. Now, let us say that I am getting one rotation matrix with respect to some inertial frame of reference. That can be one more IMU that is placed at an inertial location, a location that is not moving, okay, assumed to not move. By the way, there are always movements, but I am assuming that this point will have relatively much less movement than the movements that I am interested in measuring. Okay. And then I am measuring R2, which is also measuring the rotation matrix with respect to that earlier, the previous, the only other inertial reference frame. Okay, I am getting these two. Let us say the first one is measuring an angle of 20 degrees, the second one is measuring an angle of 60 degrees, right. Then I will have two rotations, right, and represented as cos 20 0 sin 20 0 1 0 and minus sin 20 0 cos 20 as the first rotation matrix, and the 60 rotation matrix will look like this, right. Now, if I multiply R1 and R2, if I multiply the two rotation matrices R1 and R2, I will get, you will have to do the actual computations for 20 degrees and 60 degrees and input the actual cosines and sines and do the actual multiplication. You will get the value of theta, the net rotation, as 80 degrees. But suppose I am multiplying the transpose of this rotation matrix R1, I am transposing and then multiplying it with R2, then I am going to get theta as 40 degrees. So, the total rotation that is happening, I am getting as the product of the net rotation that I get from the product of R1 and R2. But if I am interested in relative rotations between R2 and R1, if I am interested in relative rotations, I multiply R1 transpose with R2, and whatever is the rotation matrix I get, from that I try to get the angle, and that angle I will get as the difference between these two. So, if I am interested in finding relative rotations, I will have to use transpose of the first matrix, rotation matrix, right. Something to keep in mind is the order of the Euler angles. The sequence matters. If I have three principal axes, what are the various ways in which the order can go? Let us write those out. I can either have x, y, z, or I can have x, z, y, or I can have y first, y, x, z, or I can have y, z, x, or I can have z, x, y, or I can have z, y, x. If the principal axis is not repeated, right. Then these are the various ways orders in which I can find the Euler angles. These are the various Euler angles possible. If the orders are not repeated, if the axes are not repeated, I am going to have these 6 possibilities. I can have other cases where the one of the principal axis repeats, then it is going to be a complicated problem to deal with, which we will not discuss as part of this video. So, we will stop here. In this video, we looked at composite rotation matrix and how to convert rotation matrix to Euler angles, and how we can use rotation matrix to find relative orientations. And we also just began our discussion or just touched upon one example of the case of gimbal locks. Okay. With this, we come to the end of this video. Thank you very much for your attention.